a lot for inviting me here and talk about quantum random number generators, which is right now my favorite subject. It is so cool that more or less half of the things that we do in my group, and I'm the head of quantum cybersecurity group in Gdańsk, is about random number generation. I also started a company that builds random number generators, and we're very happy now because our prototype left the lab for the very first time a week ago, and it was presented and it worked. So I will show you a picture and in a celebratory mode because of it. Okay, so random numbers. First of all, we quantify randomness by entropy. This can be Shanon entropy or any other collection of entropies. For the purposes of this talk, this is not very relevant. The basic property of almost any entropy is that if it's zero, it means there is no randomness and everything is totally predictable. And if it's log n, when n is the number of the outcomes of an experiment that we can observe, then log n is the maximum. And for almost all entropies, they scale from 0 to log n. And in my talk, I will be using a lot of phrases like a lot of entropy, close to log n. No entropy, no randomness, close to 0. It doesn't matter with Shanon's view because it's the most famous one. Okay, what do we use randomness for? Science, gaming, and cybersecurity are the most important applications for us. And this is a picture taken from SMBC Comics, and it makes fun of a problem that happens in social sciences. Social sciences are heavily funded in Nordic countries. So a lot of experiments are done there and not in other places. So the results of these experiments are true for not of the countries, not generally the rest of the world. So we might say that the sample choice for this experiment is done with bad randomness. The entropy is low in other cases. So we have 7.5 billion people. So entropy is not log of that. It's much lower because the chances of picking some girl or chance are larger than picking somebody who's not Scandinavian. Okay. Second, gaming. Now, this is Robert Mugabe. He's from Zimbabwe, and he used to be a president of this country. And while being the president, he won national lottery. There are no proofs that he knew the numbers beforehand, but it's given that corruption in Zimbabwe has its own entry in Wikipedia. This is highly probable. So good randomness in gaming is also very important, and actually gaming companies love quantum random number generator, especially in online gaming. The companies that have online lotteries, they suffer from lack of trust of the users in their random number generators. If you lose 5 times in a row, you get angry and sure they are cheating. But then you feel reassured because on the first website, there is a big spam randomness provided by this and that quantum company. So this is another application in cybersecurity. I don't have to tell you much about it because this is one of the most obvious uses of randomness. And every time your computer, tablet, or cell phone starts a new thread, it has to allocate random place in memory for it. If it's not very random, it opens avenues for hacking attacks. Whenever you choose a password, it has to be random for somebody who wants to guess it. It doesn't have to be random for you, obviously, but it can. This is what the button choose a strong password for me that Chrome has, for example, uses, but it should be random for your adversary, somebody who wants to hack your account. And this brings me to the third slide, but before third, there is the second. So I would like to tell you about a book. This is one of my favorite books. I've never read it, though, because obviously it's not very hard to read. It's from 1947, and it's simply what the title says, 1,000,000 random digits. So choosing random numbers is very difficult. You can roll a dice, you can pick a number, and these are actually not bad numbers. But if you do this several times in a row, not only you're producing randomness at very low speed, but also the quality of it is really, really bad. If you write 1,000 digits and then run it through a software which estimates its entropy, I guarantee you it will be very, very low. So why do we need a book with random numbers? First of all, sometimes we don't care if everybody else knows the random numbers. So, for example, in science, if we pick people for our social experiments by the digits from this book, the concept that we have in cybersecurity, it's called security through obscurity. So imagine that I say, okay, as my password, I will pick first digit from every page. If you know that I did it, then this is a very bad password. But if you don't know this is an extremely strong password. It will be 100 or so random digits, and nobody will be able to guess. So this also has its uses, and it's not only from 1947. Although we now have much better tools, we still use public randomness. We have these things called randomness beacons. These are some agencies or organizations which produce random numbers of good quality and broadcast it over the internet. Of course, you shouldn't use it for your password, because then everybody knows it. You shouldn't use it for the keys or the lottery. Or actually, for the lottery, it might not be such a bad idea, but then, of course, you would have to trust the agency which provides this randomness. But the thing is, while I'm mentioning this specifically, is because a lot of quantum protocols are actually not generating random numbers. They can be used to translate public randomness from, for example, randomness beacons to a private randomness. And this is very cool property. Okay, so before I get to quantum numbers, I just want to talk about this question, random for who. So I would divide randomness into three kinds. Public, and this is, for example, random digits, then exclusive. So this is the case of Mugabe. This lottery, for me, the outcomes of the lottery were totally random. At least the numbers, I could predict that this guy would win, but I couldn't predict with which numbers. But for these guys, they weren't random. And there's this true randomness. By true randomness, we really mean a number which comes from an experiment such that no entity in the universe can predict this number with certainty. Maybe somebody can predict it with 60% probability, maybe 80%. It doesn't matter. It's just better or worse randomness, but it's still true randomness. And this is a quantum seminar. So quantum theory is a perfect thing because they have the division into these three kinds of randomness inbuilt in its formalism. So if I measure in computational basis, public randomness is just pure state, and it's an eigenvector in computational basis. Now, mixed state would be Robert Mugabe, maybe using even a true random number generator to pick a number and later announce. He knows which of it is. I don't, so for me, it's a mixed state. And true randomness, you probably guess it, is a pure state, which is an eigenvector of a different basis. If I measure it in computational basis, no entity in the world can predict its outcome. That's true randomness. So, obviously, not only quantum mechanics is the only theory which has intrinsic randomness, it's also inbuilt in its formalism. So obviously, using quantum devices for generation of randomness seems a good idea, and it's not a very new idea. A lot of people have it. So it's actually an entry from Wikipedia on hardware random number generators. If you go to Wikipedia, you will see a list of possible devices that generate random numbers. They are divided into classical and quantum. Actually, I think the list is much longer. I just took a part of it. And the problem is, how do you decide? I give you a device. How do you decide if it's quantum or not? My laptop, it uses quantum effects in its transistors. Can I call it a quantum computer? Well, I should. But when it comes to quantum random number generators, people do exactly this. So actually, every quantum random number generator currently on the market shouldn't be called that. Let me show you an example. So here on the quantum side, point 3 is photons traveling through a semi-transparent mirror. If you think about generating random numbers with a quantum device for 5 seconds, this is the first thing that you will come to your mind. So you have a mirror, you send a single photon. If it passes and passes with probability 50%, this detector detects it. If it doesn't, the other detector detects it, and you have a random number generator. And actually, a company, DeQuantizing, was recently bought out by SK Telecom, which is a South Korean company, and they built a device based on this idea for a new Samsung Galaxy quantum telephones. They actually have a quantum random number generator according to this idea, but other scientists like me had this idea. We gave it to the engineers, and they took the idea and started to think about, hey, okay, so This is quite expensive to build. These APDs, avalanche photodiodes, they are expensive. And I want to make them as cheap as possible so Koreans can make more money. So if one detector clicks, then we know that the other didn't, because we assume there's only one photon, and we play with the parameters of the lasers and the mirror and the lights that only one of them clicks. So let's just get rid of one of the detectors. We operate in rounds, and if in one round the detector doesn't click, we assume that the other would click. So we build our device like this. But then they look, hey, but there is this laser beam going from the laser to the avalanche photodiodes, and there are some losses in the environment. Then there are losses when you're in the detector. Sometimes the detector doesn't detect this photon, and the mirror, what it is actually doing, it's introducing more losses. So actually, we can get rid of the mirror and just make the environment and the inefficiency of the detector play the role of the mirror. So you can do it like this. And then people say, okay, now I'm an engineer, I know how this avalanche photodiode works. So basically I have there some gas or whatever, and I put a lot of voltage to both sides of the gas chamber, such that if a single photon passes through this chamber and excites a single atom, it will be enough for the electrical current to pass. And if I increase my voltage, sometimes I will observe these dark clicks, which mean that these are photons which come not from the detector, but from the background, or the detector just might create this click by itself. So by playing with the voltage, I can just make the laser obsolete. And now I have this for my random number generator. To be honest, the Koreans stopped here. They still have a laser diode in their system, but it's not really necessary. They just have it because if it's like this, then it looks really stupid. And also, if you look at it like this, actually, this diodes, noise in a diode was in Wikipedia on the classical side. So basically, is this quantum? Well, not really. So the problem I see now is that the public and a lot of scientists and engineers don't really know what quantum is, or even if they know, they pretend not to know it, to abuse this word, because quantum sounds cool and it sells. So I use quantum tablets for my washing machine because it sounds cool, and there was this James Bond quantum movie, so quantum is good. So, but the problem is that it's not only them who have problems with quantum technologies. Let's look at NCSC white paper on quantum technologies. NCSC stands for National Cyber Security Center, and it's the British government agency responsible for advising other government agencies about security in new technologies. And they looked at QKD and they said, don't use it. So the only problem, the biggest problem we have with current cryptography is that when quantum computers are built, they will be able to break almost every encryption currently used. So one option is to use QKD, but actually QKD introduces a lot of other problems. So agencies like NCSC advise that we should use quantum safe cryptography. What they mean by that is a different version of classical algorithms, which are more cumbersome and therefore not so widely used, but with an advantage that so far we don't know any quantum algorithm that is allowed to break it. So it looks like a better solution. But this is what they say about QKD. Let's look what they want to say about QRNG. They are also saying that you shouldn't use QRNG because let's look at the last one. The embedding within classical circuitry also means that QRNGs are potentially subject to a similar range of implementation level attacks as classical RNGs. And this is basically not true. This is true for all the pseudo-quantum random number generators, the random number generators which are actually classical and only have quantum in the name. A true quantum random number generator should be like a quantum computer. It should do something that its classical counterpart cannot, and what they can do here is they can be invulnerable, difficult word for me. They can be made impossible to attack with these attacks. So what are these attacks? Attacks on classical RNGs. I'm actually going much slower than I thought I would, so I wanted to talk about 15 minutes about this slide, but I will go much faster. So there are a lot of really cool attacks on random number generators. This is my favorite one. Scientists showed that if you take Ivy Bridge processor of Intel, which has inbuilt random number generator, and then you go to a factory which makes it, and then this little part, which is marked by Trojan area, is this random number generator. It's composed of several transistors, which are in a microchip. So they are really small, and change the dopant levels of some layers in some of the transistors, then it will make the numbers still look random, but it will be not random to Robert Mugabe, who made these changes in dopant levels. And this cannot be, these changes are several atoms. You cannot even see it under a microscope. So if you have a company and you buy some chips from a manufacturer, even if they look like they've been done and you check it under a microscope exactly like you told them to, there is no guarantee that they will behave like this. So this is a very potent attack. There's nothing we can do against it in classical theory. Then this is the Enigma machine. So this is also one of my favorite ones. I just wanted to mention that after the Second World War, the British sold this machine to its former colonies, claiming that it's impossible to break. So the sellers should also not be trusted of cryptographic devices. This is Snowden files. One of the things that Edward Snowden leaked was that NSA designed a pseudo-random number generator, which was not really random for them. And then they made NIST, which is a National Institute for Standards and Technology in the US, to approve it as a good random number generator. And moreover, then with this approval, they went to RSA Securities, the larger seller of cryptographic devices in the world, and convince them to set this random number generator as a default. And so in this sense, you cannot even trust a person who designs an algorithm for you. Finally, you cannot see it very well. This is Huawei router. You know what's wrong with that. So you cannot basically trust your devices at all. And moreover, there are these active attacks. Even if you have a random number generator, which is working very well, it sometimes can malfunction, and this malfunction, sometimes it happens just on its own. There was a random number generator used by NATO military, which started to produce randomness of very low quality if it was too cold outside. So this was a problem, and this is an active case of an active attack, which changes environment on purpose. So what you see here is white dots correspond to zeros and black ones to ones, and it's an output of a random number generator. When they shine some electromagnetic radiation on it, you see that they can bias the distribution towards zeros if the power is strong enough. So all of this is a big problem. And on quantum random number generators, there are other attacks. And but I want to say that this is for the so-called quantum random number generators. So, okay, I don't have enough time. Basically, they are very similar to the classical ones. So what can we do to be secure against these attacks? Because this is what I'm advertising. And the first idea is to use Bell inequalities. And this is, so I hope you all know what CHSH inequality is. Basically, if you have an experiment with two parties sharing an entangled state and they get inputs X and Y and outcomes A and B, there is this quantity here, which with classical resources should always be smaller or equal to. With quantum resources, entangled states, it can go up to 2.82. And the amazing thing is that if you think about this, this inequality has this property which we sometimes call self-test. If we observe the maximum violation, we know that the state has to be exactly like this. And if a state is like this, we know it will be zero. This is maximum state. And if we have a pure state which is not entangled, we can have what is this inequality doing is it's telling me which of these states I'm in, and tells me whether the randomness produced here is public or maybe it's exclusive. Well, about this it doesn't tell me, but it can tell me the most important thing. Do I have true randomness? Actually, if the inequality is violated, there is plots from a paper. You see that if this value is greater than 2, I have some randomness measured by some entropy, in this case, mean entropy. The cool thing about this is also curve C. It says no signal. It means that even if quantum mechanics is not true, but we only trust in some insights that we have from relativity, namely that we cannot send signals faster than light, it still means that if this is violated, we have some randomness, but slightly less. This is an amazing thing. And the most important thing is that, look, here I'm the only parameter I have is this beta. I don't care how this source is built. I don't care what state it has. I don't care how the detectors are built. Maybe Robert Mugabe with Huawei together build these devices. I don't care if they violate CHSH inequality. I have randomness, and this is what's perfect. And unfortunately, to violate CHSH inequality, and I mean without any loopholes, it's still a very, very difficult task. And only recently some experimental groups did it, but all of them did it in very, very low temperatures with fridges costing hundreds of thousands of euros. So a device like this, you cannot put into Samsung Galaxy. It's just
not really to satisfy locality conditions.
Not really. Locality conditions are needed if you want to test nature itself. So what you really need is you need to assume that there is no communication between the two detectors.
Okay.
And then if you go open your device and see that there is no wire between them, or maybe even a slab of lead, this is enough for a cryptographer. It's not enough for somebody saying, "Oh, nature is deterministic, and all the violation of Bell inequality can be explained by some fast communication."
You need to look into the box.
Yes, you have to look into the box, but still you don't need to look under a microscope to check every single part. You just need to see that there are two separate parts without any communication between them. And this is quite, in my opinion, an assumption quite easy to swallow, because if these two parts have some radios and are communicating covertly between them, it's actually much easier to build just one radio and send all the signals to the eavesdropper. So there is this standard assumption in cryptography that we have secure laboratories, and it basically means that no information leaks outside of my lab without my control. And now if I just say, now I actually have two labs, both of them in the same box, but there is a clear division between them, I can apply this secure labs paradigm to these two boxes. So yeah, okay. So the problem with this is that it is very expensive to build this. So with friends, we came up with this idea of device independence. We just add an additional assumption to make an experiment easier. Now we have Alice sending some signals to both photons, single photons, and by making some small assumption about Alice's device, we can provide security. Now, our first idea for this small assumption was a bound on the dimension of the Hilbert space that the qubits, the quantum systems are encoded in. We tried to argue that by looking at sender's device, it's possible to put an upper bound. I don't know how reasonable it is. It seemed a good idea in 2011. Later, there were other assumptions, but all of them suffer from the same problem. And the problem is that the semi-device independent experiments have this structure. There is a source, it sends a signal, it goes through some inputs, and it goes to the detection. And now, if all the inputs can be somehow communicated to the detection part, then the detection can simply fake randomness. It can have in the simplest case, a pen drive built-in with very good random numbers, which are obviously known to this creator, and it just produces them in sequence. And there is nothing we can do about this unless we somehow are able to limit the communication from the inputs to the detection. And in the device-independent case, which is this bell inequalities, the structure looks different. There is source and two separate places with inputs and the detection. And the security comes from the one and only important assumption here, and this is what Konrad actually mentioned, that there is no communication from what the inputs on the right-hand side to the detection on the left-hand side and the other way around. So, but this is cheap and this is expensive. So what can we do to make a cheap version of device-independent thing? And this is what our company does. So we have this thing with a work named Delphi. I will explain on the next slide. The source sends signals to the inputs, and they go to the detections, but they interfere with each other. And now we assume that this interference region, and it's not black, it's marked gray, to specify that we have to put some trust in it. And the only assumption that we have is that this interference region actually does nothing else but interfere the signals. So, for example, if I want to build a Mach-Zehnder interferometer, because this can be, for example, a Mach-Zehnder interferometer, the interference region will be just a beam splitter. And if I look at the beam splitter and I see that there is no hidden computer in it, no hidden laser, no hidden dial or whatever, I can safely assume it's only doing interference. So I think it's a good trade-off between these two cases. And Delphi stands for dishonest electronics, physics honest but imperfect. So, and this honesty means that I trust that interference region is only doing interference. Physics are imperfect because I don't need to specify parameters. I don't even need to know the parameters, like what are these inputs actually doing to the signal. I don't need to know what are the properties of the detectors. No, I only need to know what is the probability distribution of detections here conditioned on the inputs. I will tell about this in the next slide, but the most important thing is that I assume the electronics are dishonest. I assume every detector here, every electronic component actually has a microcomputer with powerful AI trying to lower the entropy of the whole device as strongly as possible. Moreover, they are collaborating to do this. The only thing that I forbid them to do is that they cannot communicate with each other among the lines which are not here. So, for example, if there is a signal from the source to the input, then of course the AI, malicious AI, which controls my source, can send some information to the inputs, but information from the detection station cannot go to the source because there is no communication line there. And this is the most important assumption. And why this works, I have, okay, so this is what I said in the beginning. This is our prototype. This is how it was supposed to look like when we hired industrial designer a year and a half ago, and this is how it looks in the real life. Now it's covered, and it's actually producing random numbers. If you look very closely here, you don't see it on the screen very well, but it actually gives the amount of randomness, security, and other parameters here. So it's actually self-testing itself. And how it works? Look, you know Marzender interferometer, and you have two arms, and if the phase is the same, so there's no phase difference between these arms, all the whole signal should go to one of the detectors. Now, if you change the phase in both of the arms, all the signal has to go to the other direction. But if you change the phase in only one of the arms, then half of the signal goes to each of the detectors. And if my signal is just one photon, then I will observe a click in one of the others. Now, what we can do is by looking at probability with which, in these cases, we observe a photon in a detector which shouldn't observe it, we know how we can put a bound on how much these AIs that we envision working in all these black boxes can lower the entropy, and they cannot do much. At least if the results are close to perfection, then the loss of entropy is a couple of percent. So I think basically I was very happy to accept the invitation to the seminar, because I really wanted to advertise not really my company, but this new way of thinking about security. So there are a lot of security paradigms yet to be discovered, and don't let people tell you that device independent and maybe semi-device independent are the only choices. There's a lot of choices. Delphi is one of them, and I want to finish now with encouraging you to try to look for your own security paradigm. Thank you.
Thank you, and it's time for questions.
Yes, here's about the Delphi loophole and the other one, the detection loophole.
Okay, so closing the detection loophole is why device-independent protocols are so expensive. Because actually, if you don't care about the detection loophole, you can buy a device from some companies that violates Bell inequality. And actually, in Gdańsk, we have one in the lab, but students broke, so I don't think it's but it used to work. Anyway, so it's not a problem. And here, the detection loophole is not a big issue, because what we can do is we can increase the mean photon number in the source to such a level that my detectors almost always click, and then I can gather also statistics for the cases where both of them detected a photon. And okay, I actually have a lot of notes about this and really nice calculations, which I can show you, but the bottom line is that there is no problem with detection efficiency loophole. We basically estimate the real detection efficiency and also the fraction of the cases where the detectors detect a photon but decide not to tell us about it because they are malicious, only from the statistics for the clicks. Because actually, if this is actually quite funny. If you make your source send more photons, for us, the optimum is around, the mean photon number is optimal around 3 photons or so at the detectors. Then you have single clicks, no clicks, and double clicks for these 3 cases, and it gives you 6 independent numbers, and it's really difficult for these AIs that we think are hiding to mimic these numbers. I know it's pretty vague. I can show you the exact calculations later.
Okay, we have an online question from Rafael. Rafael, please unmute yourself.
Okay. So Marcin, so in short, can you just think about your interferometer as a beam splitter, which you can either set transmission to 100% or 0 or 50, yes? It's equivalent to this.
Yes, but the important thing is that I can set it non-local. So none of the inputs knows whether I am setting it to 0, 50, or 100. Because if, say, first of the left detector gets 1, it knows, okay, it cannot be 0%, it can be 50 or 100, but I'm not sure which. So my answer is yes, but with that important distinction.
By the way, when you said that you add phase in both arms, then you should not say that anything changes, because nothing changes then.
No, but I said phase in opposite directions. That's what I meant.
Oh, okay.
So phase
I guess we need to
0, 0, and 1, 1
quantify
is minus pi half and plus pi half.
Okay.
So 1 is pi half.
Yes.
Not pi. Okay.
Yes. And on the one hand side, it's minus. I should have explained this. Sorry.
Okay. Another question. Yes, please.
I wonder about what fit. Isn't it a problem that if I want to bare test my randomness, then I need to choose 2 different measurements in one arm with another, and to choose them, I need to do it randomly. So I need another random
with a public randomness from Randbook, for example. So this is what I'm very happy that I got this question because I wanted to mention it and I forgot. This is one of the uses of public randomness. If I have a bell test and it takes randomly as inputs X and Y, then it can be a public randomness and the outcome is a private randomness, but it might look not really nice for you because what happens is that what am I going to do? Sit with a book all the time and choose these numbers? But there is a great idea by, I think, Miller and Shi. They showed that if I have 2 random number generators and just start one with, say, public randomness, then I can feed the randomness from one as the input to the other, and from the other to the first one, and this gives me infinite amount of secure randomness in a loop. So this is not a problem, and in our next prototype of the device that we are building, we will actually have 2 detectors, 2 generators feeding each other randomness. So there's no problem like that.
So I need only 1 external bit of randomness?
Well, bit is probably, it's okay. In theory, yes, there is a paper from Barcelona from some time ago when they showed that if there's only 1 bit of randomness in the universe, then the whole universe can be amplified to be totally random. So in theory, yes. In practice, because of the finite length and everything, you need a lot, but only once. You just start it with, I would say, a megabyte, and then let it go. Okay, maybe even kilobyte would be enough, but something of that order.
Can you say something about your source and detectors?
Okay, so I can, but what I can is that they look totally different that I do it here. So it's not Marcin interferometer, it's Sagnac interferometer. So, but I didn't want to draw Sagnac here because it makes explanation more complicated. You just take you can just take my word for it that everything for Sagnac works the same as for Marcin. And
But it's harder to introduce a phase shift in a Sagnac.
yes, but I actually have two experimentalists in my company who started it with me, so I don't care.
Okay.
Like they don't, I'm sure they are not sure how these numbers appear. So yeah, we have good division of work.
Okay.
One more question from students.
But I am not fully satisfied. Do you use avalanche photodiodes?
Yes.
You do.
Yes.
And photon pair sources or just a coherent source?
Coherent source, yes. And the coherent source with a large mean photon number.
So coherent source and single photon counting, basically.
Yes. Yes.
Okay. Thank you.
But we are taking into the account the case that there might be more than one photon at the detector and so on. We just assume that our detectors do not distinguish between one and larger amount of photons. If they detect the photon, they don't know how many photons they did detect. But they might lie to us about this later.
Okay.
There's one more in the back.
I imagine that losses introduced somehow makes this randomness worse, and it's not just a technical difficulty, but it's like it makes it worse on the fundamental level. So how do you tackle?
Okay. This is sort of standard thing, and I actually had a slide where I wanted to mention this, but I just skipped it. So what you do in practice in almost every random number generator is that it generates some entropy, and almost every random number generator at the beginning is biased. It produces more zeros than ones or the other way around. So there are these classical functions called randomness extractors, and they are proven that if you add extra randomness, it can be public randomness from Roundbook and have entropy well estimated, then you have a mathematical proof, then the outcome of this function is a perfect randomness. So this is why entropy estimation is so crucial. Not only you know whether your device is working or not, but if, for example, somebody comes and cools my device or kicks it, or something happens in such a way that it starts to produce less randomness, the device will see it and change the randomness extractor to one which is working with this concrete value of randomness. So this will work. And since you asked this question, let me show you this picture. So actually, this is what DeQuantizing is doing. If you have this random number generator, and one of the detectors just detected a photon. What happens if this photon is, I think the correct word for it is primed, and then it's slightly more likely to detect a photon in the coming next rounds. And this makes the probability distribution biased to be, so if you have the outcome 1, the next outcome is also more likely to be 1. So to get rid of this, you have to use these extractors, and the plot I was showing here is from a paper which shows that some company underestimated this effect of after pulses, and the randomness it was producing was lower than expected, and then they were using wrong randomness extractor and so on. So yeah, things like this.
Okay. We probably should be finishing soon, but there is one more online question. Please unmute yourself and ask the question.
Okay. My question is, when we were discussing first the classical random number generators and the part about not trusting the vendors, it's I mean, if you want to put aside their intentions of any company, whether it's classical or producing classical or quantum random number generators, and also putting aside the experimental errors of trying to build such random generators, is it a matter of security protocols, or does it have to be complete randomness in order to have that certain level of security? I mean, if we are talking about this limited randomness in the classical or limited entropy in these classical generators, wouldn't it up to a certain point be enough for this security, or does it have to be like complete randomness in order to achieve such?
It could be complete randomness. So actually, what happens, what we want to be secure against is that I choose, say, I choose a password, and somebody wants to break. If my password is 4 digits long, I can probably break it just by testing it long enough as a possible combination. And if it's 100 digits long, you can use a supercomputer to do this. And now the case is very simple. If it's 100 digits and if they have perfect entropy, then the entropy is 100 bits. If you have 1,000 bits and they have only 0.1 entropy per bit on average, then you also have 100 bits of entropy, and it would take a supercomputer the same amount of time to break this code. So basically, if you have a low randomness, you can simply use longer passwords or longer cryptographic keys and achieve the same result. So it's not a big problem if your randomness is not perfect.
Okay, I think we should finish at least the formal part of the seminar. So let's thank our speaker again.